Take two because my pizza came in the middle of the last one. Okay, so consider a father pushing a playground merry-go-round. He exerts a force of 250 at the edge of the 50-kilogram merry-go-round, which has a 1.5 meter radius. Calculate the angular acceleration produced when no one is on the merry-go-round and when an 18-kilogram child sits 1.25 meters away from the center. Okay, and we'll consider the disc to be, or the merry-go-round to be a disc and no friction. Okay, so the only force acting on the merry-go-round is the father pushing it around. Okay, and he's applying a torque, right? Force perpendicular to radius. Okay, so I'm going to use my net torque equals I alpha. All right, remember that's just like net force equals MA, but it's something that's spinning instead of moving in a line. Okay, so torque is FR. Okay, I for a disc, all right, if you look on your sheet, right, it's going to be 1/2 mr squared. That's just like the one that's the cylinder, right, but it just has a really small length, and that doesn't matter anyway, times alpha. Okay, so then alpha is going to be F times R, make that a capital R2, 1/2 mr squared. Okay, I'm not going to cancel those R's, although I could. You'll see why in just a second. Just to make it easier later. So 250 newtons times 1.5 meters over 1/2, 50 kilograms, 1.5 meters squared. Okay, so on the top, yikes, sorry. I'm going to have 250 times 1.5. So on the top, I'm going to have 375 Newton meters. That's the torque. Okay, and then 0.5 times 50 times 1.5 squared. And on the bottom, I have the rotational inertia of 56.25 kilogram meter squared. Okay, so 375, 375 divided by 56.25 is about 6.7, okay? And just so you can see the units, okay, remember a newton is a kilogram meter per second squared, okay? And then you have another meter, which is that one, and then you have a kilogram meter squared, okay? So you have all of these cancel out, and you basically have like nothing over second squared, which means it's a radian, right? Because a radian is kind of like the unitless unit, okay? All right. So that's the angular acceleration, okay? Now, if we put a kid on it, we would expect that it's going to be harder to move it. It's not going to accelerate as much if there's a kid on it, okay? So when you add the kid to it, what you're doing is you're changing the rotational inertia, okay? So I'm just going to start from this line because the dad still is pushing the same, okay? But now we have the rotational inertia of the merry-go-round plus the kid sitting a distance away. Okay, so that's like an mr squared point mass, right? Because that's also that, and this is m of the kid now. Okay, all right, so this is all the same. This is the same. Okay, right? Plus, now we have the kid's mass. Okay, and the kid is 1.25 meters away. Okay. So now we're going to add that on there. So you see that's making the bottom of this bigger, which overall is going to lessen the angular acceleration. Okay, 1.25 squared. So we're going to add another 28.13 down here. Okay, and then we're going to get 375. Oops. Well, I guess I can do that all because I have the fancy calculator. The parentheses. 56.25 plus 28.13. Okay, now I only have an angular acceleration of 4.4, okay, right? Because my I value has gone up, right? So my acceleration is going to go down under the same torque applied, okay? All right, so that's how you're going to use, right, this that we talked about last time. That's now how you're going to sort of use that in practice, okay? All right, that's that one.